now.
You're live?
Yes, I do.
Hello, I warmly welcome you to our 75th webinar by the Academy of Space Renaissance International. My name is Sabine Heinz, and I'm the person responsible for our webinar series. And on this 3rd of February 2025, I'm really delighted that you have to come to join us. And our today's special guest is Professor Dr. Jason Arnold. Hello, Jason. Welcome.
Hello. Hello. Good morning. How are you doing today?
Yes.
Buongiorno, guten tag, buenos dias, whatever works for everybody. It's nice to be here today. Thank you.
It's so nice to have you here, and it's a pleasure for us to have you here. Professor Arnold will speak about space elevators, the green road to space. Uh, it's a really interesting topic, and I'm really curious to learn more about this. I also would like to welcome Adriano Altino. He's our vice president and co-founder of SRI and former president of Space Renaissance International. Hello, Adriano.
Hi, very welcome, Jason. And I'm also very curious to listen to your presentation. And yeah, we're leaving for Vienna tomorrow to attend the COPUOS Committee for the Peaceful Uses of Outer Space, the Scientific and Technical Subcommittee. We will have several presentations and yeah, we will see what is the climate over there. Also, a very geopolitical complex situation now. Okay, so
Thank you,
please,
Adriano.
Sabine, go ahead.
Uh, Jason, before I give you the floor, I would like to introduce you to our audience, if you don't mind.
Of course.
Professor Dr. Jason, or HEP, Arnold is a Mid-Atlantic Regional Director for the National Space Society and the Director of Education and Outreach for the International Space Elevator Consortium. He serves as a member of the board of directors for both organizations. Professor Arnold is a National Space Society Space Ambassador, and previously he was a dean of the Defense Security Operation University. As a professor, he taught at the National Defense University and Air Command and Staff College. Professor Dr. Arnold is retired Air Force colonel. Jason, I'm really happy to have you here, and may I ask you to share your screen, and the floor is yours.
Thank you very much, Sabine. I really appreciate that. It's really exciting to be here. As Adriano was mentioning, some of this presentation will be also offered as evidence at the United Nations Committee on Peaceful Uses of Space. This will be a longer version of that statement that'll be given there in Vienna. Let me share my screen and we'll begin. Today's presentation I like to call Elevate. How we can have a sustainable space access for all. And we'll be talking about a variety of issues, including the architecture and structure of a space elevator, as well as some of the challenges and other things. And first, let's start with the why. What is the problem, if there is one, about space access? I think everybody who's joining us today can agree on one thing, and that we believe that space is humanity's future for a lot of different reasons. Humanity is always reaching out and finding new places and then adapting to those new environments. Right now, our primary way of investigating the new frontier of space is by using rockets. But rockets have intrinsic limitations based on just the science of reaction to getting to space. These include the fact that basically it's dangerous and they are also very dirty. And this makes it difficult for long-term sustainability, as well as the fact that they can't lift a lot because they have to carry enough fuel to carry the fuel to lift the payload. We'll talk about that more here in today's presentation. In order for us to have true accessibility into space, we really need routine, regular, safe, clean lift into space. And the space elevator, I believe, is really how that is going to occur and really take us to the stars. We need to build a permanent infrastructure rather than just be dependent on these one-use rockets that will provide us with a lot more capacity in logistics so that we can do the kinds of projects that are being proposed today. So we need fundamentally a cheaper way of getting to space, one with more capacity, and one that's cleaner for our long-term sustainability. So let's talk first about what are those limitations of rockets. They're really good for lifting people, but they really have limited capacity. Only 4% of launch pad mass ever gets to low Earth orbit, and that's just barely on the rim of the well. 2% of launch pad mass can get to geostationary orbit, and only 0.5% of launch pad mass actually can get to the moon and Mars. So we have to, it's an incredibly inefficient way. It's the only way we have, but it is incredibly inefficient. And as a result of that, only about 20,000 tons have ever really been delivered to LEO from 1957 to 2020. You know, the kind of things that we want to do on the moon and Mars are going to require huge capacities for logistics, not just for the initial development and building and construction, but also for sustainment and for supply. 500,000 tons is estimated to be required for the moon base, and maybe 1 million tons are required to build something sustainable on Mars. And of course, the amount of pollution that's created by rockets is not good for the Earth. In 2021, 1 million kilograms of black carbon pollution were released directly into the stratosphere. And because these are going into the upper atmosphere that's much more stable and doesn't have much mixing, they hang out, those particles hang out a lot longer. As we try to put more and more stuff into space, it means that we're going to have more debris and more pollution in our higher atmosphere. And we're already dealing with the consequences of what we have there already. So where did the idea for the space elevator come from? Real quickly, go back to 1903, and the pioneer of astrophysics, Konstantin Tsiolkovsky, who in 1903 came up with the idea for the rocket equation that everybody uses today. In 1895, before he came up with the rocket equation, he postulated about a tower that could reach geosynchronous orbit and use gravity to anchor a tether that a tower that could be climbed up and down. Well, of course, a tower's materials would be so heavy that it would collapse on itself, and this idea was further refined in 1960 by Yuri Artsutinov, who was published in the Pravda, and then Jerome Pearson in 1975 that talked about this ability to have a counterweight in geosynchronous orbit connected to an anchor on the Earth and a cable between the two that could connect and bring things up into space. So the famous writer Arthur C. Clarke picked up on this and came out with a paper in 1979 on the space elevator thought experiment. And for many of us, that was our introduction to the idea of a space elevator, was his famous science fiction novel, Fountains of Paradise, which was a fictional account of the building of a space elevator. And that's pretty much where things stood. It really was a idea that was in the science fiction realm. It wasn't really until 2011 and a little bit before, when 2003, when Dr. Edwards, and I'll show his book in a moment, was paid by NASA to actually produce a book exploring the concept. And then 2011, my organization, International Space Elevator Consortium, did a paper saying it was technically feasible. And then now in 2023, we're looking at it being ready to start development. So there's a lot of space elevators in science fiction, And that really is where people got these ideas. And it wasn't until recently that we started to look at it in science fact. And the main reason why is because the technology for the tether. We can build the anchor with today's technology. We can build the space station in orbit with today's technology. We can do it all. But the big question was the extraordinary strength needed by that tether that connects the two. There just wasn't any material, nothing even close. Well, that's changed, and I'm going to go into some more detail about that today. But these three books, these are basically the source material for the information that I'm giving you today. The 2003 study by Dr. Brad Edwards on the space elevator, and this was funded by NASA, their Institute for Advanced Concepts. And then the International Academy for Astronautics published two books. These are very scholarly books with the findings of scientists and engineers that did specific studies on the challenges of elevators. So these are two excellent volumes that go into great detail and great specificity about the feasibility of the space elevators. And both of them conclude that we're ready to begin this right now, and the technology does currently exist. So this was in 2013, and then another publication in 2019. For those of you who attend the International Space Development Conference, the next one's in Orlando, I think in June. We will have a presentation on this material, and we'll also have copy of these books that are available. So what is a space elevator? I've been talking about it like you know what I'm talking about. So let's just break it down into the component elements and give you an idea of what the modern day space elevator looks like, as opposed to some of those early ideas uh, that Konstantin Tsiolkovsky and Art Sudinov and Jerome Pearson had years and years ago. So the first thing is to have an equatorial sea-based platform. The space elevator has to be located because of the peculiarities of gravity, has to be located on the equator. But locating it on a sea-based platform gives us the ability to have some mobility and use dynamics of the tether. The apex anchor is basically a huge space station that acts as a counterweight out at geosynchronous orbit. Geosynchronous orbit, of course, begins around 36,000 kilometers away. It's very high. And that it is a position that has a constant zenith or a constant silhouette on the Earth. It orbits directly above the same geographical point on the Earth. This is, of course, extremely important, and to have an elevator work that you're exactly over the point that you're starting from. This is connected by a cable, or what we call a tether, of an immensely strong substance that can maintain the spectacular pressures that are going to be exerted by the gravitational force of the Earth. Essentially, a space elevator is a balance of two things: the Earth's gravity with the centrifugal force of the Earth's rotation. The Earth rotates about 1.5 kilometers a second, or 1,076, I think, kilometers per hour. And so it is throwing this counterweight around at incredible speeds, but that gravity is being counteracted by the centrifugal force of that counterweight that's being hurled around the Earth. And that's what gives the inherent stability of a space elevator. It's a fascinating and elegant concept because in the rocket situation, we are using explosive reactions, basically strapping ourselves to a bomb in order to fight gravity and overcome it with explosive thrust. In this situation, we're actually using gravity as the solution for holding this very stable um, tether in place so that climbers can operate up and down. And because it has this stable base, these climbers can operate electrically, which gives no pollution at all. So that's the concept of the modern day space elevator. One of the other key things about the modern day space elevator is rather than just stop at the geostationary orbit altitude of 36,000 kilometers, we can actually spool out even further out to 80, 90, 100,000 kilometers. Why would we want to do that? Because the further you go out, the faster you're moving. And if you are at the counterweight, at the apex anchor, you're moving with all of this speed from the Earth's rotational force. If you think about holding a rope with a weight on the end and spinning it around your head, as you reel out the rope, that rock at the end is going faster and faster and faster. Well, what happens when you release it? It goes spinning off on whatever vector you released. All that rotational energy that you've built up into that rock is now captured in velocity. So what does that mean for us? It means that if you have a spacecraft that is at the counterweight and you want to send it off into space, you simply release it. And it releases at the speed that it was swinging at around the Earth on whatever vector you want. So if we're at 36,000 kilometers, we're going about 3.7 or 8 kilometers a second. Now that is velocity that you don't have to use any fuel for. All simply by releasing from the counterweight, you have all that velocity. If you go out to 100,000 kilometers, you're releasing where you're spinning around at over 7 kilometers a second, maybe 7.8 or so kilometers per second. This is so incredibly fast, and there's no fuel involved. So whereas before we would have had to use fuel in order to get to that speed, all we have to do is let go of the counterweight at exactly the right vector, and we'll be tooling along with basically the captured rotation of the Earth. This is the concept behind the modern day space elevator. So, as I said, the difference between reality and fantasy has to do with how we get this tether built. And this has only happened recently. Even in that first book I showed you by Dr. Edwards, they were looking at carbon nanotubes. But carbon nanotubes are very difficult to grow at the kind of length that we need. So what's different now is that we have this material that we call graphene superlaminate or GSL. This is a 2D material of carbon. So it is a kind of graphene. It's carbon. It's grown in a single layer, a single crystal, one atom thick on copper foil. It's seeded using the chemical vapor deposition process, and it's seeded on a copper foil. We'll talk more about the GSL in just a moment. Another challenge for the space elevator is weather. You've got this tether that's going up through the troposphere. It's going to be exposed to storms and winds and lightning, all of that. So how do we protect from that? Another issue would be debris. How do we protect from the debris that's floating around in low Earth orbit, as well as micrometeorites and what have you, that could possibly come and damage the tether as it through a strike? This is a problem for all spacecraft and all satellites. They're all now subject to this danger from orbital debris. And of course, costs. Building a permanent infrastructure is going to cost a lot. And the solution to that, I believe, is through international co-production, through a similar process as we did with the International Space Station. This would be an endeavor the like of which has never been seen, and I believe it could actually help us retain some additional global stability and security. Let's talk about that material first. This is such a new thing. The descriptive language about what it actually is still evolving. By the way, this material comes from Adrian Nixon. Some of you may know him. He's publishes the Nixine Journal, which is dedicated to advancements in this particular material. This material is going to be revolutionary. I mean, it's not just about the space elevator. Having a material this strong will be a game changer for everything we know. I like to use the example, this stuff is so incredibly strong. It's basically diamond strength. It's transparent and it's thin, so it's very light. It is the miracle material. The problem is it's so difficult to make. We haven't been able to get it evolved into industrial scale. We can make this as much as like a meter a second or 2 meters a second. I mean, a minute rather, a meter a minute, 2 meters a minute, but it's very difficult. When you take one layer of this and then you take several other layers of this crystal graphene and then you stamp them together, you get a phenomenon using the van der Waals force where they link between the layers. They create the same bonds between the layers as they do between the atoms in the top. And what that creates is basically similar to a three-dimensional carbon solid, which is a diamond. So imagine that. You have a ribbon made up of layers of carbon crystals, single crystals, diamond stamped together for a type of super strength that has never been seen before. The type of strength that we need for this tether is in the nature of 100 gigapascals. This graphene superlaminate that we're making, and we've been able to do about 30 layers up to now to get these layers pushed together. The type of strength that we're getting from this is well over 100, about 120, 130 gigapascals, which is incredible tensile strength and more than enough to build the kind of permanent infrastructure space elevator that we want to make. So the big deal is, how do we do it at industrial scale? And that is what they're working on now. It grows on a layer of copper foil. You have to get rid of that copper foil, and then using what they do in manufacturing, what they call the roll-to-roll process, eventually we'll get this to the point where we can create it at scale. Once that happens, that's the last piece. That's the last piece that will create the tether that we need to actually build the space elevator. So this is the process that needs to be created so that we can move on. Now, just to show you, I'm not making this up. This is actually happening in the real world. It's been happening for a while now. This comes from the Nixine Journal. The source is down there. You can look it up yourself if you like. LG and Charm Graphene. They are making this now. And you can see the copper foil there on the left, that they're doing that at 1 meter per minute at lengths up to a kilometer. These are not necessarily single crystal. They are what's known as polycrystal, which is still an incredibly strong. It does have some what they call border grains where the crystals meet, but it's still an incredibly strong material. And when layered, it increases the strength. So I'm going to move to the next challenge, which we talked about before, which was weather. This is the recorded tracks of tropical storms. If you notice, because of the Coriolis effect, which moves storms, you can see them all moving either to the south or to the north of the equator. Well, because we're going to build on the equator, that's where our Earth base is going to be. It's not going to be a huge deal to be around storms. So you can see it's almost completely empty here along the equator. So that's one way to avoid the storms. This is commercial airline traffic. We don't want to run into those either. If I'd like to call your attention, if you look off to the west of Central America and South America, you'll see a huge dead area where there are no commercial airline traffic. That's the area that we want to place the base, the sea base for the space elevator. And finally, this is lightning activity. And you can see the light pink and the white is virtually like less than 10 strikes. I mean, so virtually no strikes are happening in the white and light pink areas. Again, I take a look off of the west coast of South America and the South Pacific, and you'll see that there is an area that is empty. So by sticking on the equator to the west of South America, in that calm zone, or what I like to call the Goldilocks zone. It's the perfect zone. There is no problem with weather. There's no problem with lightning. There's no problem with commercial air traffic. So that would be the way we would avoid those challenges. This is a close-up of that area right along the equator, just to the west of Ecuador and to the west of the Galapagos Islands. That is the proposed anchor zone for this. And the anchor itself, it's sea-based. We have the technology now to do this. Essentially, we're building huge, enormous um, oil platforms and other discovery resource excavation platforms throughout the world. This is a technology that we more than have the ability to do. The reason why it's so important is because we can, by moving the sea base a little bit, we can use the dynamics to move the tether, and that would avoid debris that would cause damage. The material, as we said, is very strong, and since it's a wide ribbon, most meteor strikes or debris strikes will just punch a hole like a hole in a card, which is not great, and over time would deteriorate the overall tether, but it's not going to destroy it. The larger debris is what we really worry about, and we're tracking that. We're tracking the larger debris. So we'll know when it's coming, and we'll be able to actually position the tether out of the way by manipulating the sea-based anchor. So those are some of the solutions and mitigations that we would use for these extreme challenges that we would face with the um, tether. So the last piece about the money, the cost is going to be huge. It'll be in the tens of billions of dollars. And really, it's a lot of it's unknown because we don't really know how much the tether material is going to cost. We know it's feasible, and we, based on looking at how human beings do things in the past, once it gets to scale, once you can see that you're using this material for things like phone screens and TV screens and windshields and all this other stuff, the economies of scale kick in, and the manufacturing gets cheaper and cheaper. But it's still, I believe, going to be in the tens of billions of dollars to build such a structure. But I think that it's the only way that we're going to be able to lift the kinds of millions of tons that we need to get into space, and also have the access to that velocity capture from the rotation of the Earth. So international collaboration for me is the only way this would work. And there's another reason why it needs to work. Sometimes when I talk about this, people go, "Yeah, but what about wars?" And people, you see, if one nation controls this space elevator, they own access to space. So it is much better if we can have an international, a global kind of common ownership of a permanent infrastructure like this, where nations that don't even have a space program can pay a toll and lift whatever they want into space. This is the great equalizer about a space elevator, because only a few nations now have the money to afford a space program. What a space elevator does is it makes it possible for all nations to be able to go to space and be able to access the new space economy. So international collaboration is incredibly important. It means that this will be built and operated collaboratively, which means if everybody has an interest in doing of this space elevator doing well, then there's no reason for it to be a targeted or attacked. It means that we get the benefit of the entire globe's expertise in all these different areas that needed to be studied, the modeling and simulation for the dynamics, the directed energy to operate the climbers, debris mitigation, the materials research, directed energy research, all of that. We can get nations to specialize and focus on those areas, commit all their resources to just that area, and therefore, have a much greater um, uh, commitment from the world, and also uh, a much greater chance that we'll have a better and better product with this space elevator. Modular construction, just like we have the ISS, you could have pieces of the apex anchor could be built by different nations and operated by different nations. The potentials are extraordinary, but I think one of the key things, and why I'm talking to you today in this forum, is international collaboration is the key to a space elevator, ensuring that access for all. That global partnership is what is going to create the stability and ultimately the security for the space elevator. We have all these great plans for humanity, and some of them are critical to our survival as a species. Planetary defense. We know there will be an asteroid or comet coming. We are already having these zip by the Earth on a regular basis, and we don't see them until most of the time we don't even see these uh, near Earth objects until they're already past us. If we're going to have a chance to survive longer, like than the dinosaurs did, we need a planetary defense system. That is millions of tons that needs to be lifted into orbit so that we have ability to have interceptors or some other system to intercept a near Earth object that could destroy us as a species. Space solar power, human settlements, zero and low gravity manufacturing, resource extraction of asteroids and what have you, moon regolith, all of that, deep space missions, spacecraft construction, space tourism, all of that is really it's only ever going to happen if we have the space elevator. We need to get away from Leo. We need to get out into really deep space to where we could actually operate, manufacture, do the kinds of things that we need to be doing as a species to really truly be a interplanetary, multiplanetary species. Just to give you an idea, even Musk is estimating that it's going to be around 1 million tons of cargo to build a self-sustaining city on Mars. And as I've said before, as a former logistician for the Air Force, building something is just the beginning. There's a lot more than just building it. You've got to sustain it, and you've got to supply it, and you've got to continue to develop it. And that means millions and millions of tons. Um, One of the things that a space elevator also facilitates is this idea of being able to link with an Aldrin cycler, another spacecraft that's on a permanent orbit between Mars and Earth or the moon and Earth. A space elevator could send tenders from the apex anchor to the cycler back and forth as a way of enabling a almost railway between the planetary systems. Space-based solar power. This is a huge thing that we could power our planet with. Uh, Multiple gigawatts of power could be sent to the Earth, but we are talking about a solar reflector that could be up to 3 kilometers wide and weighing over 80,000 metric tons. How is that stuff going to get lifted in by rockets? It's just not feasible. So hopefully you see the problem as well. Um, so it's feasible. The science is there. We know the science works. We know that we have the materials and technology to build it. Uh, we just lack the will. That's the only thing that really is missing. And a lot of that has to do with the paradigm. We've been so long in this world where rockets were the way that we're going, even in our movies and our books, it's always blasting off. And I get why that is the case, because honestly, there is nothing cooler than a space launch. There's really, if you've been down there and watched it, there's nothing cooler than watching a rocket explode and just go right up to it is an amazing thing to watch. But part of the reason there's so much tension and excitement about it is it's just like anything else that's cool. It's dirty and dangerous. It's loud and dirty and dangerous. And that's why we get such a thrill out of seeing one of those. Really, if we're going to be a species that is going to space and operating in space and doing the kinds of things we need to do, what we really need is to make it boring. It needs to be like a commute. It needs to be like going into your office building and calling for the elevator and going up. That is really where we need to go in order to get the kind of success and advancement that we need to do as humanity. So we need to embrace that paradigm shift. We need to engage our students and public on this alternative way. And I'm going to tell you, This is happening now. If you're noticing, you're seeing more and more in books and movies that feature space elevators, more YouTube videos. Many of you are probably familiar with this. The picture that's shown here is the Japan experiment where they actually had a tether with a little robot climber that went back and forth. So they are actively looking at these kinds of things right now. So that is something to consider. So that is my presentation for today. Hopefully you have enjoyed what we had to say. I'm going to hand it back over to Sabine for any further comments or questions. Thank you, Sabine. I'm going to stop sharing now.
Yes. Thank you so much, Jason, for this interesting lecture, and I appreciate that you were speaking slowly. I could understand, fully understand you. It was so nice. Yes, you speak a very clear English. But I have a question. I
Okay.
didn't get the point. With the anchor, you have this tether fixed with the anchor, and then you release it, and it is like a catapult, or
So that's a great question. Thank you, Sabine. Um, so you have a base on the Earth and you have a counterweight. That counterweight remains attached. But if you were to build a spacecraft in space attached to that counterweight, and then you released that spacecraft, the counterweight remains.
mm,
Counterweight remains. But if you release that spacecraft, then it will zoom off on whatever vector it released from. It will zoom off on a tangent
mm,
from that circular orbit. Uh, and it will have the velocity of the Earth's rotation.
mm,
So just like if you were spinning that rock around your head and then you just let go, that rock is going to go flying straight ahead wherever you released it, and it will have the rotational energy that you had built into it. So essentially, a spacecraft that released from the counterweight, if it was held onto it and then it released, it would go zooming off at the speed of its rotation. Now, like I said, the Earth rotates at a certain speed, but the further out you get from the Earth, you're going farther, right? Because your
mm.
radius of that circle is larger and larger. So as you go further and further and are spinning further and further from the Earth, you're having to go faster and faster. You might remember, when ice skaters do that they get into a line and then
Yes,
they
yes,
have the,
yes,
the last person's on the edge and
yeah,
then you let go and they go flying off with all the speed.
yes,
The person in the middle is barely moving. They're just barely turning, but
yes,
that person on the outside just goes flying away. And so that's the counterweight remains, but
yes.
the spacecraft leaves. I hope that answers your question, Sabine. Thank you.
Yes, but you have, I still have, so you have this tether in the anchor. You let it spinning around and it goes into space.
No, the whole
And
thing doesn't go
you
into.
have the space station there. You release it and then it is going spinning around.
No, it stays continuing. It continues to turn. The only thing that you're releasing is whatever space vehicle is attached to it. So the counterweight's still there. The space vehicle, the counterweight still continues to go around with the tether, but the spacecraft releases from it and it captures the motion
Yes,
of the
but
that
how
that
comes it from the Earth to this point?
Okay, so that's a great question. One of the things about the space station is that you could do manufacturing at the space station. So you would have a climber that goes from the anchor. You have an electric climber that goes up the tether and it carries tons of equipment from the sea base up to the tether. That climber is what brings the material. So you could take a spacecraft and build it modulars and take up the modules into space, assemble it in space, and then let it go. But
Okay.
that's the climber is electrically powered. There's a lot of different architectures. I didn't go into it at length because there's so much uh, there's so much about the climber and how it would be powered.
Okay, you have like an elevator. The climber
Yes,
is the elevator. Okay, then I get it. But if you pass the atmosphere, you need a heat shield protection,
yes.
and yeah. So Yeah, okay. Elon Musk has reusable rockets, so that is possible. Okay, so this goes up and down, but
Yes.
with electricity.
It is
So you
essentially a
need,
space, it's a spacecraft, Sabine. It is essentially a spacecraft, but it's attached to the tether, and it goes up and down. It's reusable. It goes up and down over and over again. The design for it, if you're interested in it, if you go to isec.org, isec.org, and go to the research, if you look at any of those books, there is thousands of pages of research on what a climber would look like, how it works, how strong the wheels need to be, how many wheels you're going to need, the the pinch, the mechanism to hang on to the tether,
Mm.
the motors, how it would be powered. Right now, the number one kind of architecture they're talking about is a directed energy laser beam that powers the electric motor that sends the climber back and forth.
so
The
do you have
Can I?
Yeah, sure.
two tethers because it I know with electricity. Okay, not like an elevator and a little bit different.
Yeah.
Okay. Um,
There are many different architectures that are here. I can only just give you the basic concepts
In,
in such
Yeah,
a
yeah,
short
but
briefing.
it's
I
really
think I
interesting
have.
because I was always thinking how it works and okay, the space debris,
Yeah.
it's another problem. And I don't know if you have been in Germany. Do you know what Materialermüdungserscheinung is?
No.
Uh, when the material gets I translated literally when the material gets tired. Also, if the material,
Radiated.
yeah, yeah, and
Yeah.
how
That's
long?
another that's another thing we studied, Sabine, not to interrupt you, I'm sorry. The that's another thing we studied. And of course, the tether is exposed to radiation. These are areas that we still need to study, because radiation will eventually affect it. Carbon is very resistant to it. It looks like it's going to be very good. But yeah, they're looking at the life cycle of how long do we have before we have to replace that tether. All of those are I mean, there are very advanced scholarly studies on each of these materials and the life cycle. And I just all I can say is look at these books that I showed, go to isec.org, go to research. All this stuff is there. We also have it on the National Space Society's Space Edge Academy site, and you can look at it there too. So I mean, there is really outstanding work done by international scientists, um, that will anybody who is a geek like that and loves engineering and science really should go to that site, and you will find everything that I really didn't go into today because I just don't have the time. Adriana, did you have something too? I'd heard you trying to break in.
Yes, of course, it is. It is a very complex matter, and it is impossible not to try to go deeper in the technical,
Yes.
some technical details. So I have a couple of questions, very ignorant questions, however. What speed, what velocity will be required to travel these 36,000 kilometers? It's a long distance, and we have to go very fast in order not to be climbing forever, you know what I
Right,
mean.
right.
So this is
Well,
a first question about the velocity that is needed. Second question, the electrical power to move that the climber. I think it will be very, very important, a huge amount of electrical power needed. So what would it be, what will be fed this power? The power supply will be from Earth or from space, from photovoltaic panels and so on. And I think that we are okay. We are talking. Third question, we are talking about a climber, no? So a climber is based on some mechanical mechanism, because there will be some wheels that will move on the tether in order to make the climber go up and down. So
most of the material that you're talking about, they're very specific studies. We have it on the ISEC site, but just to give you just an idea, there's a bigger concept I want to make sure you understand. It's not just an elevator. We need what we call a dual access. We need rockets. Rockets are really good at certain things. We need both. We need rockets and the space elevator. It's not either or. And we see the space elevator for is more like cargo, because you are right. It's going to take a long time to get the climber up to 36 and even 100,000 kilometers. And the faster you go, of course, the more heat that you're building up on the mechanical system, just as you said. And of course, heat's a problem when you get outside the atmosphere, because you have to figure out how to dissipate that heat. Because in
Yeah.
a vacuum, how are you going to dissipate that heat? So these are really good questions. And we have an entire group that is focused on just these issues within the Space Elevator Consortium. And they publish probably more than anybody else. So you will find a lot of information, including how many pairs of wheels are going to be required, what material are those wheels going to be made out of, that so that they don't break down, how often can they go back before they have to be replaced. All of those things are what they're looking at. Um, there's different things about the power, because I want to talk about that too. But most of what we're talking about is beaming directed energy at a voltaic panel and converting that into energy for the climber motors. Um, as far as about whether it's going to be done from the Earth or space, my personal feeling is it needs to be both, because you need a different kind of laser that's going to be able to penetrate the atmosphere. A different color, a different wavelength of laser is going to be needed in the troposphere and stratosphere and up into the vacuum. Once you get into the vacuum, there's a lot less attenuation of the laser, right? So you could have uh, the laser on the Earth would be able to power you just till you get out of the atmosphere, and then it could take over from space. Of course, that gives you the problem of having uh, a counterweight shooting a laser down to the earth, which may not be the best idea, right? Because you got a powerful laser shooting down at the earth. That's not necessarily the best thing. But if it's at a wavelength that breaks up in the atmosphere, then you wouldn't have to worry about it damaging anything on Earth. And there would be almost zero attenuation of the space laser from the apex anchor, because it's in a vacuum. It's traveling in a vacuum. So, but that's just an example. If you go to the site, you'll see there's dozens of different ideas about how to power this, including possibly a Hurst engine or things like that. I hope that answers your question. I did or your questions. Was there anything that I missed or that we wanted to?
I have
I
another question.
okay, okay,
Uh,
go ahead.
and another question is it thought, so now it is developed for cargo, but maybe for space tourism, it could
Yes.
be also an opportunity.
Yeah, that's what the reason I'm talking about it as a dual access is because rockets are probably always going to be the best way to move humans. And part of that has to do with the fact that we have to pass through the Van Allen belts, that's where we don't have the protection of the magnetic shielding, and we're exposed to a lot of cosmic radiation. So
Mhm.
in a rocket, you're moving so fast that you're only exposed for a short time.
Mhm.
In the space elevator, you would be dragging up through that a lot slower, and it would mean that you would have to have a climber that was specialized just for people and that was carrying mostly just shielding.
Mhm.
And then those people that would travel in that climber would have to be put into some kind of status or anything, because they'd be in there for like a week.
Mhm.
And that goes back to your point, Adriana. How fast does it have to go? I mean, the velocity is really dependent on what you're moving. If it's a human being, it's going to be needed to go pretty fast.
Mhm.
But we're kind of understanding that humans would probably be best served traveling to space on the rockets, and then the cargo would be moved by the space elevator. Another great thing about a space elevator as opposed to a rocket is a rocket has to smash its way through the atmosphere. So what we can carry on a rocket is really limited by the fairing. It's got to fit inside the fairing. So we have these we have all these origami things to keep it small enough to fit in the fairing. That wouldn't have to happen with the climber. As long as the load was balanced, you could have long stuff, you could have short stuff, you could have almost any shape. As long as it was balanced, it could be taken up. And that, if you could imagine you're trying to build some kind of huge habitat out in space, you might have these enormous spars and things. Like you could take those up on a space elevator. You would never be able to take them up on a rocket. So
That's
it's
true.
not just the weight, it's also the size and the volume.
Cool, very cool. Oh, I thank you so much. And I would like to invite you because we have also an academy in our Space Renaissance society and with different topics. And I think we could open, Adriano, what do you think, a space elevator because we have space habitats as a working group or an academy
Why
part.
not?
Hmm?
Yes, yes, that
Yes.
would be interesting.
Yes, I'm responsible for our art chapter, so and I know what I would transport with the elevator, books and paintings and artwork.
Yeah. Yeah, and
Um,
that's the thing that I'm a logistics guy from before, and when I look at space and what people want to do, I'm like, look, this is all dreaming until you figure out the logistics of how to get it there. I mean, even when we were as a species exploring our own planet and traveling the seas, we couldn't do anything with the New World until we understood how to move things there. And we had many disasters where the transportation just wasn't there, and settlements like Roanoke and Virginia, what have you, they didn't get supply, they didn't get sustained, and they all died. That would be such a terrible thing to happen on the moon or Mars. And I don't think that we can really think about those kind of communities and settlements unless we have already figured out how we're going to move millions of tons. So this is kind of a first step that I feel we have to make before we can ever really think about dreaming about those kinds of settlements, which we all think that we need to do. I really think everybody agrees that
I
we
can
should be a
convince you,
multi-planetary.
if we have more time, then I can convince you why we have to take art and books
Yes.
to space.
Yes. Oh, I agree. I agree. But as long as we're just doing rockets, you'll never be able to do it because they'll say, no, we've got to take this or that instead because it's just too expensive. It's something like 6,500 dollars to get a kilogram into orbit. Um, you know, this would be, we're estimating you would get this cost down to 100, $200 per kilogram using a space elevator. So that's when you're talking, we can really do this. We can really do this.
Let me know, then I will send something with the elevator. But would you accept our invitation so Adriano can provide you with more information? And it would be really, really nice to have you as part of our organization, and because it's really an interesting topic, and we don't have it so far, and we would like to learn more. And I think we would find people which would like to work with you, and yeah.
Well, I think Adriana will tell you one of the reasons why we're here today is because as a director of education outreach, ISEC signed on with the Space Renaissance Initiative. So my organization ISEC is part of it, and I look forward to continuing to work with you, Semyon. And I
Oh,
think we're we're
great.
coming up on our hour. Are we good to go?
Yes. Okay. I thank you so much for being here with us. It was really nice and entertaining, and it was really a good lecture. And I thank to our audience for being here with us. And yeah, I hope to see you soon. And I would like to invite you also to our next webinar. It's about the uh, meteor which was fallen in Germany. We have two German guys, and they are really, really, yeah, engaged and you would like them too and to listen to. It's in 2 weeks at 9 o'clock at the same time, and they will talk about the meteor who has fallen in Germany and how they found them and how they were connected. And yeah, it's also a very interesting topic. Thank you for being here with us, and thank you to our audience. Adriano, thank you for joining and for helping me.
Thank
And
you.
I wish
Thank
you
you,
all a
everybody.
nice week.
Yeah. Okay.
Bye.
Okay.